Okay, everybody, the last section for Business Cal is section 8.3 called Local Extrema for Functions of Two Variables. You did local extrema in Cal 1 for single variable functions where you found local min, local max. You actually did it a couple different ways in Cal 1. You can see section 3.4 and section 4.1b in our software or in our book if you want to go back and look at that. So the difference with this is we have literally three-dimensional objects now. In Cal 1, everything could be drawn on a flat plane. So some terminology, local min, local max, again, which you've seen before, and a new thing called a saddle point. A saddle point is not technically an extrema, but it's a point that's going to show up from time to time in multivariable functions. So what I want to start with is just some basic functions that show you what each of these things are. Okay, so let's take the function z equal x squared plus y squared. If I graph that, here's what the graph would look like. Okay. So notice, I can move it around some here if we want to. Notice that your z values as you go from the bottom up are increasing. So I've got the graph rotated the correct way. But there's a low point at the very bottom of the graph, right where I'm putting the cursor there. That's the lowest point on the whole graph. Everything else is above it. Okay, so that's considered a local min. Alright, a local max, maybe something like this next function I have written here, negative x squared minus y squared plus 10. Let me show you the graph for that. It's basically like the other graph, but it's flipped over. Okay, so again, let me situate it like this. Notice your z values are getting higher and higher as we go up, but you have a high point on the graph now, right where I have the cursor there. So that's considered a local max right there at that high point of the graph. We could rotate this around all we want, and we're still at that high point right there. Okay, the third type of point you're going to get is called a saddle point. So something like this last function I have here, x squared minus y squared plus 5. Let me graph that. So saddle points literally get their name from like a saddle you put on a horse. The idea is this. Again, I have this situated correctly so my z values are going up. Let's rotate this graph like that. If I look at this point right here, it's basically at the top of an upside down U shape. Okay, so I have where I'm going with the cursor there, I have like an upside down U shape. So I have a high point there. So looking at it from that direction, you might say it looks like a local max. Well, let's flip the graph 180 degrees or 90 degrees, I guess. Let's look at it from the other direction. Okay, this is that same point right here, but now it's at the bottom of a U shape. So it looks like a local min from that direction. So again, the idea is a saddle point looks like a max from one direction. The point's right there where the cursor is. We rotate that around. Okay, there's that same point, but now it looks like a local min. So a saddle point looks like a min from one direction and a max from the other direction. Okay, so what we're going to concern ourselves with is working on these multivariable functions and getting the local max, the local min, or saddle point. So let me pull up Hawks here. This is what the questions look like. Find all local maxes, local mins, and saddle points for the function. Write your answer in the form x, y, z. If you have more than one, you put a comma in between them. So you've got 3 boxes here for each type of extrema or saddle point. If you don't have a particular type of point, you click none beneath it. Okay, so let me show you how to do the test. So first thing we're going to do is, I'm going to call this the D test, incidentally, just to give it a short name. The first thing we're going to do is find our critical points by setting f sub x equals 0 and f sub y equals 0. If you remember in Cal 1, you found something called critical values in Cal 1, and you did that by setting the derivative equals 0. Well, remember, we just have 2 different derivatives now, so we're setting them both equal to 0. And then solving for x and y. Okay. Once you get your critical point, you can go ahead and calculate a z value from that. Calculate z by plugging x and y into the original function. Alright, so that's going to give us the point. Remember, these are the way these are asked is they're all points written x comma y comma z. Okay, so you've got your point x comma y comma z at this point, or there might be more than one point. But you still got to go through and figure out how to classify it. Is it a max? Is it a min? Is it a saddle point? Right, so the way we're going to do that is with the d-test. What we'll need is the second derivatives. Find f sub double x, f sub double y, and f sub xy, or f sub yx. Remember, those 2 are the same thing. Okay, so and we can make a value for what's called d. The reason this is called the d test is we're going to calculate a value called d. This is not a linear algebra class, and the formula for d actually comes from linear algebra, so it's a little bit above what we would do in BCal. But basically, d stands for determinant. You may have dealt with matrices in high school in algebra. You can get a determinant of a matrix by multiplying through values in a certain way. So this formula is going to come from it. I'm not going to write it out, but the formula that we're going to use, we can just use it as f double x times f double y minus f sub xy squared. That's going to give us d. Alright, then I'm going to set up a table here. D can be one of 3 things. It can be a positive number, it could be a negative number, or in rare instances it actually could equal 0. So there's 3 options there for what D comes out to. Alright, if D is greater than 0, if D is positive, then the test actually follows the second derivative test, which was in Cal 1. In our book, that's section 4.1b. What you would do is you would look at the second derivative, more specifically f sub double x, if it is positive, you're going to have a local min. If it's negative, you're going to have a local max. In the rare instance, it would equal 0, which none of the questions you're going to get, this won't happen. We wouldn't be able to tell. There's some other methods to find local extrema in multivariable functions. Unfortunately, we don't get to them in business cal. So technically, you're going to have that, but again, you're never going to see that possibility. The ones you're going to get will work out. Okay, so that's if D is positive. If D had come out to be negative, then you don't have to look at anything else. You just automatically have a saddle point. So you don't even have to look at any second derivatives. It's just if D is negative, saddle point. If D actually equaled 0, it's sort of like f double x equaling 0 here. We can't really tell. So there's other methods to go through to try to figure out what you have. Again, for us, we're not going to have that option. Everything you're going to see is going to work out to be a min, a max, or a saddle point according to this test. We just don't go far enough to get into any of the other methods because obviously this is the end of the semester. Okay, so really you have three things to remember. If D is negative, saddle point. Okay. If D is positive and f double x is positive, local min. If D is positive and f double x is negative, local max. Okay. So really just remember those three things, those three options. You're going to get a saddle point, a local min, or a local max. Okay, let's take a problem from Hawks. Okay, so they give us this function, negative 4x squared plus 4y squared minus 40x plus 24y plus 2. We want to go through and apply that test we talked about on the other screen. Okay, so to do that, we're going to have to get our first derivatives. So hold on, I'm rewriting the function. Okay, so let's go back over here. So here's our function. Remember, the first part of the test is to get your critical points, and you do that by setting f double x and f sub x and f sub y equals 0, solving for x and y. So we've got to get f sub x and f sub y. F sub x, that's going to be the derivative with respect to x, so go through and get that. So the derivative of negative 4x squared would be negative 8x. The derivative of negative 40x would be negative 40. None of the other terms have an x, so their derivatives are all 0. Okay, so there's f sub x. F sub y, on the other hand, let's see, the derivative of 4y squared would be 8y, and the derivative of 24y would be 24. None of the other terms have a y, so their derivatives are all 0. Set these equal 0 and solve for x and y. So in this case you have 8x equal negative 40. Negative 40 divided by 8 is going to be negative 5. Over here, 0 equals 8y plus 24. So negative 8y equals 24. Divide each side by negative 8. Y is actually going to be negative 3. Okay. So your critical point is negative 5 comma negative 3. Let's go ahead and get our z value while we're here. So second part of this, calculate z by plugging x and y into the original function. We're going to need that. Okay, so again, we've got x, we've got y, we need to get z. Z is the same as the original function. So z equals f of negative 5 comma negative 3. plug those into the original there. Negative 4 times negative 5 squared plus 4 times negative 3 squared minus 40 times negative 5 plus 24 times negative 3 plus 2. Go through and calculate that. Alright, I get 66 when I plug that in. So your critical point is negative 5 comma negative 3 comma 66. Okay. So we've got to go through and figure out, is that a local minimum, a local maximum, or a saddle point? Alright, so to do that, we need to get our second derivatives and plug them into this formula for D. So again, we're on this third step here. Alright, so let's come to the side here. F double x, you need to be looking at f sub x, which was negative 8x minus 40. Do the derivative again with respect to x. That's negative 8. We need f sub, let's go ahead and get f sub xy while we're looking at f sub x. There's no y's in negative 8x minus 40, so the derivative with respect to y would be 0. And we also need f sub double y. Okay, so here's f sub y, 8y plus 24. Derivative with respect to y would be 8. Okay, so there's our second derivatives. Plug into that formula for D. Again, that's f double x, which is negative 8, times f double y, which is positive 8, minus f sub xy squared, which is 0 squared. So negative 8 times 8 is going to be negative 64. Okay, so that gives you a value for D. Alright, negative 64 is obviously less than 0. It's negative. So if we look at our table here, we're going to be in the second row. If D is less than 0, we have a saddle point. Alright, so that means that this critical point you found is a saddle point. You didn't have any other critical points, so you don't have a min, you don't have a max. So let's put those into Hawks over here. Okay, so no max, no min, saddle point, negative 5, comma, negative 3, comma, 66. Let's hit submit. There it is. Alright, so that's probably the most basic of the questions. They're all going to be polynomials. We're not giving you anything where you have to do quotient rule or chain rule or logs or e's. They're all going to be polynomials in this section. So there we go. Again, get your first derivative, set them equal 0, solve for x and y, plug x and y in the original function to get z, so that gives you your critical point. Get your second derivatives, plug them into the formula for D, and based on what you get for D, you can make a judgment on saddle point, local min, or local max. In this case, D was negative, so we had a saddle point. So there we go. Alright, this is pretty much the same. I want to get to something like this where you have a mixed term here, a term that's got x and y in it. That'll make solving for x and y a little bit different, a little bit more difficult. Same process, but having to do a little bit more to solve for x and y. So let's see, we have x squared plus 4xy plus 2y squared plus 12x plus 16y minus 1. Okay. Let's go through our process. So we need to get our first derivative, f sub x. I'll start with that. Derivative of x squared would be 2x. The derivative of 4xy would be 4y. The derivative of x is 1. Let's see, 2y squared doesn't have an x, so that's 0. Derivative of 12x is 12. And the last two terms don't have x, so there's 0. So there's our derivative with respect to x. With respect to y, we would have, let's see, x squared would be 0. 4xy would be 4x. 2y squared would be 4y. 12x would be 0. 16y would be 16. Negative 1 would be 0. Alright, we set those equals 0 to solve for x and y. So here's the difference in this problem versus the previous one we worked. In the previous question, each equation just had one variable. In other words, if I flip back here and look at it, when we got right here, 0 equaled negative 8x minus 40, that just had x in it, so it was pretty direct to solve for. You just went through and got x by itself. The same thing over here, that equation just had y in it, so it was pretty easy to solve for. In this problem, both equations have both x and y in it. Okay, so what you're going to have to do is do some algebraic method to solve for x and y. Substitution is common, it'll work. There's also elimination method, which is common as well. I prefer elimination method if it works. It works with exponents of 1. So if you look at all these variables, they're all x to the first and y to the first. We could do elimination method here. So the way elimination works is you write your equations on top of each other, and you want to line up your variables. So I want to have 4x underneath that 2x. I want to have 4y underneath that other 4y. I want to have 16 underneath that other constant 12. Okay, so I've got x's on top of each other, y's on top of each other, and constants on top of each other. And the idea is this. You want one of your variables, doesn't matter which, to have the same coefficient but the opposite sign. Okay? So if you look at the y's here, these are both 4y. Okay, so they're already the same coefficient, they're both 4, but we need an opposite sign. Okay? So multiply one of these by a negative sign. Alright, you got to multiply all the way through. So negative times 0 is still 0. Negative times 2x is negative 2x. Negative times 4y is negative 4y. Negative times 12 is negative 12. I'm not doing anything to the other equation, so let's just bring it back down. Okay, so look at my y's again. I've got the same coefficient, 4, but opposite signs. One of them's positive, one of them's negative. That's what you want to happen. So you can multiply one or both equations by whatever is necessary to make that happen on one of your variables. And again, it doesn't matter which variable you're doing. I chose to do y here since they already had the same number in front of them. Once you get that, you can actually add the equations together. So 0 plus 0 is 0. Negative 2x plus 4x is 2x. Negative 4y plus 4y is 0, so that's gone. And then negative 12 plus 16 is 4. So when I do that, I've eliminated y. I have an equation that just has x in it. That means I can solve for x. 4 divided by negative 2 is negative 2. Okay, so there's my x value. Okay, we still need a y value. So you can take that x value and just plug it into either one of these original, I shouldn't say original function, but the original derivatives here, f sub x or f sub y, whether you use 2x plus 4y plus 12 or 4x plus 4y plus 16, either one you could plug into and get a value for y. Doesn't matter which one you plug into. Let's just say I use the first one here. 0 equals 2x plus 4y plus 12. I'm going to plug negative 2 in for x there. So that leaves me just a single variable y to solve for. Okay, so let's see, let's subtract 4y over. Let's see, 2 times negative 2 is negative 4, plus 12 is going to be 8. If I divide each side by negative 4, y is going to be negative 2. Okay, so it just so happens that x and y both came out to the same number this time. That doesn't always happen. Okay, you just have to work the equations out and see what it is. So don't think that always happens. Okay, so we've got x and y. We need to get z. We get z by plugging into the original function. Excuse me. So we're going to plug in negative 2 for x and negative 2 for y in the original. So that's going to give us negative 2 squared plus 4 times negative 2 times negative 2 plus 2 times negative 2 squared plus 12 times negative 2 plus 16 times negative 2 minus 1. So let's calculate that. That's going to be 4, let's see, negative 2 times negative 2 is 4 times 4 is 16. Negative 2 squared is 4 times 2 is 8. 12 times negative 2 is negative 24. 16 times negative 2 is negative 32. Minus 1. So let's see here. Add that up. 16 and 4 is 20, and 8 is 28, minus 24 is 4, minus 32 is negative 28, minus 1 is negative 29. So there's our z value. We have a critical point of negative 2, comma, negative 2, comma, negative 29. Okay, so that's the point where we've got to figure out, is it a max, a min, or a saddle point. Okay, we got to get our second derivatives. So let's see, f sub double x. So I'm looking back at f sub x right here. 2x plus 4y plus 12. The derivative with respect to x would be 2. F sub xy. Again, looking at f sub x. Derivative of 2x plus 4y plus 12 with respect to y would be 4. And f sub double y. So I need to look at f sub y back up here. 4x plus 4y plus 16, derivative with respect to y, is 4. Alright, and again, remember the formula for d, f double x, which is 2, times f double y, which is 4, minus f sub xy squared. So that's 4 squared. So let's see, 2 times 4 is 8. 4 squared is 16. 8 minus 16 is negative 16. Okay, so again we have a saddle point because d is negative. Okay. So saddle point, negative 2, negative 2, negative 29. Don't have any other points, so no min and no max. There we go. Okay, let's take a look at this problem. Grocery store sells two sizes of frozen pizzas. Managers determine that the annual profits estimated by that function in thousands of dollars. where x represents the number of size x and y represents the number of size y. Find the number of each size that should be sold to maximize profit. Alright, so this is a word problem. Use these to your advantage. The reason we give you these is you actually only have to do half of the process. Look at what they're asking down here. Number of size X, number of size Y. They don't give us any option anywhere to say no solution or none or anything like that. So when we solve in the beginning for our X and Y values, that's going to be it. Okay? We can just directly put those in. Okay, so I've got my function copied down over here. We need to get our derivatives. So with respect to x, this would be negative 0.5 times 2 is negative 1, so negative 1 x. Derivative of 33x would be 33. Everything else is 0. Piece of y, negative 0.8 times 2 is going to be negative 1.6 y. Derivative of 48y is going to be 48. Everything else is 0. We set those equal to 0. So that first one's easy. Just move the x over and you've got it. The second one, 0 equal negative 1.6y plus 48. So that's going to be 1.6y equals 48. So we just need to say 48 divided by 1.6. So let's see, 48 divided by 1.6 in our calculator is 30. Now, technically, the question was talking about maximizing revenue. We should technically go all the way through and make sure it's a local max. But again, look at how it's formatted. It's going to be the same thing on your quizzes and tests. They just want the x and y value. There's no way to put no solution on this. So once you have this x and y value here, that's it. X is 33, y is 30. Okay, so use that to your advantage. It lets you shorten the process up, and we're still able to test you on basically finding the critical points without having to go through the entire test for that question. There we go. Okay, this one, and I apologize that my screen is cutting that edge off there. Okay. Owner of a small business advertises in a newspaper and on television. He has found that the number of units that he sells is approximated by n of x comma y equal that function, where x is in thousands of dollars, is the amount spent on newspaper advertising, and y in thousands of dollars is the amount spent on television advertising. How much should he spend on each to maximize the number of units sold? Okay, so this is almost like the last problem. We get x and y, we've almost got our answer. Just remember, they want to know how much money to spend. So keep in mind, x and y are in thousands of dollars. So you're going to need to multiply them by 1,000. Okay, so you're going to do the same process you did in the previous question. Just multiply by 1,000. Okay, so let me write my function here. Negative 0.5 x squared minus 0.4 y squared plus 5x plus 8y plus 350. Okay. Let's get our, there we go. Let's get our derivatives. So with respect to x, we'll have negative x plus 5. With respect to y, we'll have negative 0.8y plus 8. Set them equals 0. So x is going to be 5. Over here, move the negative 0.8y over to the left, so you got to add it to change the sign. 0.8y equals 8. And then 8 divided by 0.8 would be 10. Okay? So these are our x and y values. But again, remember in the question, x is in thousands of dollars, y is in thousands of dollars. And look at what they're asking here. They're asking for the actual dollar amount. That's why there's the dollar sign there. Okay, so when we get 5, that means $5,000. When we get 10, that means $10,000. Okay, so that's what we actually need to answer there. So basically just multiply by 1,000. Newspaper was X, so X is going to be this one. We got $5,000, and Y was television. We got $10,000. There we go. All right, this one is probably the most complicated question you're going to see, simply because you have to actually create the function before you can do the test. And so if you read through it, manufacturer makes two kind of magazine racks, metal and plastic. The metal rack sells for $50, the plastic rack sells for $28. They give you a cost function where X is the number of metal magazine racks and Y is the number of plastic magazine racks. How many of each kind should be produced and sold to maximize the profit? So they're asking about profit, but they haven't given us a profit function. They've given us some sale prices and a cost function. So what you need to remember is profit equals revenue minus cost. So we need a revenue function and a cost function. Well, remember, they already gave us the cost function, so we have that. Cost function is 0.04 x squared plus 0.5 y squared plus 34x minus 58y plus 2540. Okay, so I'll plug that in for my cost function here. We need a revenue function. Okay, so they didn't specifically give us a revenue function, but they gave us everything we needed to get a revenue function. If metal magazine racks are X and they're selling for $50 a piece, then 50 times X, that's $50 for every one you sell, is your revenue from those metal racks. Likewise, the plastic racks are Y. They're selling those for $28. So 28 times Y is going to be $28 for every one of those you sell. Okay, so your revenue function is just $50 times X plus $28 times Y. Okay, let's simplify here before we start doing derivatives. Let's see, I like to do my x squareds first, so negative 0.04 x squared. Then I'm going to do my y squareds, negative 0.5 y squared. Let's do our x's. 50x minus 34x is going to be 16x. Then let's do our y's. 28y minus negative 58y, so that's 28y plus 58y is what, 86y. And then don't forget you still have that constant, so minus 2540. Okay, so just combine like terms there. And once you get the function, now it's just like the last couple of problems. So we'll get our derivatives. So we're going to have, for with respect to x, negative 0.08x plus 16. With respect to y, we're going to have negative y plus 86. Set them equals 0 and solve for x and y. So 0.08x is going to equal 16. So just figure out what 16 divided by 0.08 is. Let's get our calculator. 16 divided by 0.08 is 200. The other equation, just move the y over and it's solved. So they should sell 200 metal racks and 86 plastic racks. There we go. Right, so again, that's the most in-depth one because you have to create the function. Once you had the function, it worked just like the others. Okay. I'm going to take that back. This is probably the most in-depth one. I forgot about this one. Okay, a grocery store sells two brands of a product, brand X and brand Y. The manager estimates that she sells brand X for X dollars per unit and brand Y for Y dollars per unit. She'll be able to sell 13 minus 25X plus 15Y units of brand X and 27 plus 15X minus 10 units of brand Y. Find the price of each that will maximize revenue. So we don't have a revenue function, okay, but they want us to maximize revenue. So we've got to come up with a revenue function. Okay, if X is standing for the number of units of brand X, then X times that price excuse me, that's kind of backwards here, I'm sorry. She sells brand X for X dollars per unit, so that's your price. She's going to sell this many of them. Okay, so you can say the price, which was X, times how many you're going to sell to get the revenue for brand X. And we can do the same thing with brand Y. Add that together and you're going to have your revenue function. So we're going to have X times how many they're going to sell of brand X. 13 minus 25X plus 15Y plus, okay, Y is the price she's charging for brand Y. And she says she's going to sell 27 plus 15X minus 10Y units of brand Y. Alright, so there's our revenue function. Let's go ahead and multiply out. Okay, so that'll be 13x minus 25x squared plus 15xy. Over here you're going to have 27y plus 15xy minus 10y squared. Okay. Let's go ahead and combine like terms. Okay, so let's see. Let's do our x squareds first. You have negative 25x squared. Then let's do our y squared. You have negative 10y squared. Let's do our x's, 13x, and our y's, 27y. And then your xy term. So you have actually two of those. 15 and 15 is going to be 30 xy. Okay, so that's simplified. All right, get our derivatives. Okay, so the derivative with respect to x would be negative 50x plus 13 plus 30y. And with respect to y, we're going to have negative 20y plus 27 plus 30x. Okay, set those equal 0. Alright, we have the situation where you have both x and y in the equations. So you're going to have to do, again, some algebraic method to solve for x and y. I'm going to use elimination method, okay, just like I did the several problems ago where we had to solve for x and y this way. So let's write our functions on top of each other. Line up your x's and y's. So for my other equation, I want to put the x's right beneath negative 50x. So I've got 30x there. My constants will come after that. That's 27. And minus 20y goes underneath the other y. Okay, we want one or both we multiply one or both equation by whatever is necessary to get the same number with opposite sign in front of one of the variables. So it doesn't matter if you do x or y. Let's just take a look at, say, the x's here. I've got a negative 50x and a 30x. Well, I know if I multiply negative 50x times 3 and I multiply 30x times 5, I know 3 times 50 is 150, and I know 5 times 30 is 150. And one of these is negative and one of these is already positive. So that's what I'm going to multiply my equations by. That's going to give me the same number in front of x, but different signs. Okay, so multiply through. So 0 equal negative 150x plus 39 plus 90y, and 0 equal 150x plus 135, right? 135. And then 5 times negative 20y is going to be negative 100y. Add that up, your x's go away, so those are gone. 39 plus 135 is 174. 90 minus 100y is negative 10y. Alright, so that's just got a y in it. We're actually able to solve that at this point. So 0 equal 174 minus 10y, so 10y equals 174. Divide each side by 10, so that's going to be 17.4. Remember, these are prices, so that really basically means $17.40. We need an x value as well, so you can plug that y value into either one of your original equations here, where we had our first derivatives. Doesn't matter, either one we want to plug into. Let's plug into the first one, I guess. Okay, so 0 equal negative 50x plus 13 plus 30y. We know the y value, so we're going to plug that in. I'm going to go ahead and move that 50x over. Alright, so let's multiply out and add up on the right side there. 13 plus 30 times 17.4 is 535. And all we've got to do is divide each side by 50. That's $10.70. Alright, so there we go. So our y was $17.40, our x was $10.70. Okay, so for brand X, again, $10.70. For brand Y, $17.40. All right. If you have any questions about this on Tuesday or Monday, feel free to bring those. I am going to move the due date for the quiz back a couple of days, so you should see all that information in the email.